Welcome back to the channel. Today we're going to be talking about calorimetry, the different formulas that we're going to be using in calorimetry, and essentially how to answer almost any type of problem that we might see in the calorimetry portion of chemistry. So I want us to first start off with these two formulas, Q equals mc delta T and Q equals C delta T. Now, there are, I would say, about two big differentiators that will indicate whether we use this formula or this formula in a given problem. First off, the most obvious one is the fact that we have a mass in this equation here, and we do not have that mass in this equation here. So if a question gives a mass, a value for a mass, then that will almost immediately, that should swing you towards using this equation here, mc delta T, as opposed to C delta T. Another big indicator here is the definition of this C versus this C. So you might confuse the C in Q equals mc delta T versus this C here in Q equals C delta T. And they are in fact different. This is lowercase and this is capitalized for a reason. And so I want us to first start with this one. This is called the specific heat capacity, the lowercase c. And this is the quantity of heat that's required to increase the temperature of 1 gram of a substance by 1 degree. So how much heat is required to increase the temperature of a substance? 1 gram of a substance by 1 degree. So what is the substance that we're referring to here? This would be either an element or water even. And this is really quite different than the C here, this heat capacity. This is the capital C. This is the quantity of heat that's required to increase the temperature of an object by 1 degree, either Celsius or Kelvin. So here we're talking about an object. What does that mean in this case? You might not really be sure what they're talking about when they say object. So in this unit, in calorimetry, evidently you're going to be running into problems that talk about bomb calorimeters or coffee cup calorimeters, and these are objects. Obviously, these are not substances or compounds or water. Obviously, this is a solid object, and therefore we're going to be using C delta T when we deal with those types of objects. And we'll see problems where we're going to use C delta T over mc delta T. But I just wanted to get that differentiation out of the way. But typically, it's usually going to be that mass that really distinguishes whether you're going to use this formula or if you're going to use this formula. So if we're given a mass, immediately default to this formula. Now, this lowercase c, the specific heat capacity, versus this uppercase C, the heat capacity, are both always going to be positive. So that's great. You don't need to worry about the signs in this case. Obviously, we have delta T here and delta T there, so you probably will be paying attention to signs because we're doing difference in temperature, T final minus T initial, or T2 minus T1. So you obviously want to pay attention to signs for here, but for the C's, they're always going to be positive values, so you don't need to worry about that there. Now, if we talk about the units here in these formulas, we have our Q value, the heat, which is going to be in joules, okay, that's energy, and we also have it here. Final answer will be in joules, or kilojoules, which we'll talk about later, how to convert from joules to kilojoules. I'll show you how I do that quickly. We also have a mass here, which is going to be in grams, and we have a temperature here, which is going to be in Celsius or Kelvin. We also have temperature here, either in Celsius or Kelvin. So what is the unit of the specific heat capacity and what is the unit of the heat capacity then? If we look down here, we can see that the specific heat capacity is in joules over grams times Celsius, or joules over grams times Kelvin. And if we look over here for the heat capacity, it's just joules over Celsius or joules over Kelvin. Now, these units might be a bit, murky, confusing. It might be hard to remember, which one is it? What do I do? Was it joules over Celsius, joules grams Celsius? I can't remember. I'm going to show you how you can intuitively figure out which unit you're using when you're dealing with specific heat capacity or heat capacity. So let's just move down here. Let's create a bit more space. So here we have the formula Q equals mc delta T. We know our final answer is in joules. We know that the mass is in grams. We have specific heat capacity, which for the sake of our anxiety in the test, we can't remember what the unit is. Let's go with that situation there. And we know that we're dealing with Celsius degrees. We could also do this in Kelvin, but the idea remains the same. So if we know that our final answer should be in joules, that means we need to cross out this grams and this Celsius, okay? So whatever we write here has to have grams on the bottom and Celsius on the bottom so that they will cancel out. Therefore, joules has to be on the top because when these cancel out, all we're left with is joules. So specific heat capacity is going to be joules over grams per Celsius, or over grams times Celsius. Now, if we look at the heat capacity, we know, again, in Q equals C delta T, Q is in joules. So that's what our final answer should be. That's the unit it should be in. We have the heat capacity, which for the sake of this situation, we can't seem to remember. And we also have it in Celsius, our temperature here. So whatever unit that we're dealing with here has to have that temperature on the bottom because we need to cross out the temperature. Therefore, joules will be on top because when we cross out the temperatures, we're left with joules, which is our final answer there. So our heat capacity is going to be in joules over Celsius. And our specific heat is joules over grams times Celsius. So that's how we would sort of derive those units there very intuitively. You do not need to memorize. Just look at the other units next to it and you're going to know what you need to cross out. Okay, so let's start with this problem here. A flask containing 8.0 times 10 to the 2 grams of water is heated and the temperature increases from 21 degrees Celsius to 85 degrees Celsius. How much heat did the water absorb? Okay. So we have a mass, which is 8 times 10 to the 2 grams. We have T2, which is 85 degrees, and we have T1, which is 21 degrees Celsius. So we're asking about Q. What is that Q value? How much heat did the water absorb? Now we also need that specific heat capacity. The specific heat capacity of water is 4.184 joules per grams times Celsius. So this is sort of a number you're going to have to remember, but when you do enough problems, you're basically going to have this number drilled into your head and you will almost never forget it. So this is a straight plug and chug sort of situation that we have here. We have our formula, Q equals mc delta T. We're trying to find Q, so we don't know that value. We have the mass, 8 times 10 to the 2 grams, times the specific heat capacity, 4.184 joules per grams Celsius. And we have T2 minus T1, our delta T. So it's going to be 85 degrees Celsius minus 21 degrees Celsius. And this is 64 degrees. Now, if we plug all of this into our calculator, obviously we also want to make sure that our units cross out. The final answer here should be about 214,221 joules. So if they asked for this answer in kilojoules, how would we get from this number in joules to kilojoules? So what I like to do, joules, is I just like to, my favorite thing here, if you can't tell, is to cross out units. So we have joules. So that means I'm going to have joules on the bottom to cross things out and kilojoules on the top, since I want to figure out what the kilojoules, what the value is in kilojoules. Now we know that 1 kilojoule is 1,000 joules, just like 1 kilogram is 1,000 grams, right? It's just joules this time. So we're going to use this number and divide it by 1,000. So 1, 2, 3, 1, 2, 3. It should be 214.221 kilojoules, or just 214 kilojoules. That would be our final answer in kilojoules, or 214,221 joules. So that is how we would answer this question. So what exactly is a calorimeter? In its most basic form, it's a device that measures heat or thermal energy. What happens is you have a system and its surroundings, and depending on if the system is releasing or absorbing heat, either in an exothermic or an endothermic reaction, you will see a corresponding change in the surroundings and therefore a change in temperature. In this case, it's through this thermometer here. But essentially what we're doing is we're measuring transfer of heat between the system and the surrounding. And this brings me to this equation here. qsystem plus qsurroundings equals to 0. So this goes back to the first law of thermodynamics, where energy cannot be created or destroyed. It just converts from one form to another. And in this case, we're talking about thermal energy. So if the system is losing heat, then the surroundings are gaining heat. And it's essentially moving between the two, but the sum of them is going to be 0. And so if we isolate for Q system here, and we move the Q surroundings to the other side of the equation, we get Q system equals negative Q surroundings. And this equation is really, really important in calorimetry. So let's also talk about the coffee cup calorimeter then. So in an ideal situation, we only have exchange of thermal energy between the system and the surroundings. Okay? And heat doesn't dissipate out of that system or surrounding, that sort of calorimeter, if we will. But in real life, when we make our own sort of makeshift calorimeter here with a coffee cup calorimeter, this is probably what your lab does. It's probably a lab section, a portion of a lab that you're going to do is coffee cup calorimetry. But this isn't an ideal situation because we obviously didn't perfectly seal it, and so we have some exposure to the outside environment here. And so in this case, a coffee cup calorimeter is typically used during endothermic reactions and mildly exothermic reactions. So in the case of highly exothermic reactions then, like a combustion reaction, that's when we would use a bomb calorimeter. So you've probably heard of that term in class as well, and you might not have understood exactly what your prof was talking about when they said coffee cup calorimeter versus a bomb calorimeter. So these are the two cases of when you would be, focusing on a coffee cup calorimeter or when you're thinking about a bomb calorimeter, and we'll do problems with both. So let's solve this question. A 300-gram piece of metal is dropped into 400 milliliters of water at 25 degrees Celsius. The final temperature of the water is 45 degrees Celsius. Calculate the initial temperature of the piece of metal. Specific heat capacity of this metal is 0.450 joules per gram Celsius. Assume all heat transfer was between the metal and water with no heat dissipating to the outside environment. So let's start with our givens and how we're going to get to our missing variable. So we have 300 grams of the metal. We also have 400 milliliters of the water, which is equivalent here to 400 grams. We also have our T initial and T final, or T2. What we don't have is that initial temperature of the metal. We do have that T final, because what we did here was we dropped a hot piece of metal into the water and the whole thing became 45 degrees Celsius. So that is the T final for both of them. We also have the specific heat capacity here, which is 0.450 joules gram Celsius. And the specific heat capacity of water is 4.18 joules grams Celsius. So if we write out our expression here, or our formula of how we're going to find what T1 is, we start with Q system equals to negative q surroundings. This is because what this situation is describing is a system, aka the 300-gram piece of metal, dropped into the surroundings, which is the water, and there is a thermal exchange here. You can see we started at 25 degrees Celsius, the water, and it went up to 45 degrees Celsius, the full thing, the water plus the metal. So the water had absorbed some of that heat from the metal that was dropped into it. And so this is a Q system equals to negative Q surroundings type of question. And the great thing about that is, well, we know that Q equals mc delta T here because we're given a mass. So we basically just use this broken down expression of Q for the system and for the surrounding, and we just find that missing variable. So it's a direct plug and chug. So let's just write out that expression here. So we're going to have 300 grams times 0.450 joules gram Celsius times T2, 45 degrees minus T1, equals to negative 400 grams, 4.18 joules grams Celsius times 45 degrees minus 25 degrees, and that is 20 degrees Celsius. So that's where we're starting with, okay? So let's combine everything that we have here because there isn't anything missing here. The only thing we're missing is this T1. So let's simplify until we get this T1 isolated. So what we have is 300 grams, or I'll just drop the units just for the sake of simplicity. 300.450, 45 minus T1 equals to negative 33,440. Now, if we expand here, if we multiply this out, we're going to get 135 times 45 minus T1 equals 33,440. Remember, this T1 is the initial temperature of the metal because you need delta T on both sides. It's Q equals mc delta T of the system, the metal, and Q equals mc delta T of the surroundings, the water, just so that we're all on the same page. So let's distribute that 135 over to this 45 and to this T1 here. So we get 6075 minus 135 T initial of that metal equals to negative 33,440. Now we can bring this over. So we're going to get negative 135 T1 equals to negative 33,440 minus 6075 or 6075. Isolate for T1. This is going to be T1. So negative 33,440 minus 6,075. That is going to be negative 39,515 divided by negative 135. We have two negatives here, so they're going to cross out. So our final answer is going to be a positive value. T1 is 292.7 degrees Celsius. And so that's how we solve this problem here. 50 milliliters of 1 molar of aqueous HCl and 50 milliliters of 1 molar of aqueous NaOH are added to a coffee cup calorimeter, causing the temperature to increase from both being 22 degrees Celsius to the solution reaching a maximum of 30 degrees Celsius. What's the amount of heat produced by this reaction? Assume the volumes are additive. So this question might be a bit trickier this time because now we're including chemicals or compounds here. We have HCl and NaOH. It's not as clear cut as having one piece of metal and drop it into water. That was very clear, system surrounding. But now we're talking about a solution and things are getting a little bit confusing. But not to worry. Let's start with our givens, and then we'll break down how to digest this question and approach it. So we have 50 milliliters of HCl and 50 milliliters of NaOH. And they're added to a coffee cup calorimeter. The temperature, so T1 was 22 degrees Celsius and T2 was 30 degrees Celsius. So it asks for the Q, the heat. Now, we have, again, it says we have a hint here. Assume the volumes are additive. This means that we're going to be adding these volumes. 50 mils plus 50 mils is 100 mils. Now, we mentioned using Q equals mcΔT. So this 100 mils is equivalent to 100 grams because we need a mass in this case. So in this case now we have a mass, we have T1 and T2, we're looking for Q, and we also don't have C, but I'll break that down in a second, how we can sort out what the C, the specific heat capacity, is in this case. The one thing I want to make sure that we understand here is that we always refer back to this equation. Q systems equals to negative Q surroundings. So when we have our system and surroundings that are clear cut, like a metal in water, for example, this equation becomes a lot easier to do, right? You just do mcΔT of the system, of that metal, for example, mcΔT of the surroundings, which is the water. But now we're talking about solutions and reactions. What is a system and what is the surrounding in this case? That's where it gets a bit confusing. But what you can do is actually write this Q system equals negative Q surroundings in a different format now. Now it becomes Q reaction equals to negative Q solution. So that's how I want you to see this type of question. When you're beginning to add compounds and you're creating a solution, see here it even tells us the solution, immediately you want to switch to this. Q reaction equals to negative Q solutions. And this will become much, much easier to process. Now, I encourage you to, try to solve this on your own. And you will quickly realize that, okay, let me just do an mcΔT here, mcΔT here, plug and chug like we did in the other question, except you don't necessarily know what you're going to write here for mcΔT. Is it mcΔT of HCl plus mcΔT of NaOH? Is that what you're going to do? 50 grams, use both of these temperatures for both of them. It's going to get really messy and it's not going to make any sense. And that's how you know you're not going in the right direction. So I'm going to show you how to really simplify this type of problem and do this correctly. And you can essentially approach any of these types of questions where it's a reaction and a solution using this simple trick. So Q reaction is negative Q solution. We can't actually write anything here for Q reaction because we have all these, we have two compounds here. We have hydrochloric acid and NaOH that are going to combine together, and we don't have all those values, and we might not be able to extract the correct values for those. So we're going to pretend like we're going to ignore this for now, and we're just going to focus on the Q solution. Because we have values for our Q solution, we can plug in mcΔT for this Q, okay? So our Q solution is going to be 100 grams, a C value, and delta T, 30 degrees minus 22 degrees. Now, what is the C value here? Well, this is a little bit of chemistry background, but if you mix a strong acid, which is HCl, and a strong base, which is NaOH, they will undergo a neutralization reaction to create a salt, NaCl, and water, okay? So NaCl and water, H and the OH there. So this water indicates what our C value is. If you remember what the specific heat capacity of water was, it's 4.184 joules grams Celsius. So that is essentially the C that we're going to use. So it's mcΔT, 100 grams, 4.184, 30 minus 22, that is 8 degrees. So 8 degrees Celsius here. So again, this is a simple plug and chug. So the answer is going to be 3347.2 joules, something around that value, depending on if you keep that 4.184, or if you just do 4.18. Depends on how your professor or your teacher teaches it. Some teachers keep it at 4.184, some just do 4.18. So this number will sort of be approximate based on if you keep it or not, if you keep that 4 there. So it should be around 3,347.2 joules as your answer. Now this is Q solution, but we said that Q reaction is equal to the negative of Q solution. So it's going to be negative 3,347.2 joules. So that is our final answer. Q reaction equals to negative 3,347.2 joules, and that's how we solve this problem. Let's approach this question. An instant cold pack consists of a bag containing solid ammonium nitrate with an inner bag containing water. When the water bag is ruptured, the ammonium nitrate and water mix, causing the ice pack to become cold. When 4 grams of solid ammonium nitrate dissolves in 50 milliliters of water at 27 degrees Celsius in a calorimeter, the temperature decreases to 22 degrees Celsius. Calculate the value of Q. Okay, so again, let's start with what we are given here. So we have 4 grams of ammonium nitrate, which is NH4NO3. Okay. We also have 50 milliliters of water, which is 50 grams essentially. We have T1 and T2 here. So we have 27 degrees and 22 degrees Celsius, and we want to find out Q. So once again, we always start with Q system equals to negative Q surroundings, okay? And just like the last problem, this is a bit tricky because this isn't a clear-cut system surrounding. I mean, you can kind of see it a bit better here, right? It's ammonium nitrate in water, so it feels a little bit more clear-cut than the previous question where it was HCl and NaOH, and it was a little bit harder to tell. But regardless, in this question, because we're mixing the ammonium nitrate in the water, we're creating sort of new compounds together with that reaction, then I like to immediately default to Q reaction equals negative Q solution. So this is so much easier for me to conceptualize it, and I just focus on the solution, because notice that we're only given the temperatures for the solution here. We're given the water mix. So ammonium nitrate dissolves in 50 mils of water at 27 degrees. Temperature decreases to 22. So this is of the solution. There's nothing about the reaction that's given here. Maybe if you were to split these up and say, this is the mass and this is the mass, and somehow try to do mass mcΔT, just like in the previous question. But that is some way longer stepped method, and you may not even get to the right answer doing that because you'll either confuse yourself and get lost, or there's just something wrong that you're doing using that method. So I like to simplify it and stick to this. Q reaction equals to negative Q solution. So that's what I go with. So let's find Q solution. Okay. Again, mcΔT. Remember, C of water is 4.184 joules over grams times Celsius. So our mass here of the solution, beware, it's not 4 grams, it's not 50 grams, it's 50 plus 4 grams. So it's 54 grams because the solution is the water and the ammonium nitrate together. So that is why we add them. So we have 54 grams times 4.184 times T2 minus T1. So 22 Celsius minus 27 degrees Celsius. And that is -5 degrees. Cancels out. Our final answer will be in joules. And if you plug and chug, multiply all this out to find Q, it should be 1129.7 joules. So 1129.7 joules is Q solution. Now, Q reaction equals to negative Q solution. So our answer will be the negative of that number. Approximately this number, depending on if you keep that 4 here in 4.184. It depends on your professor or your teacher. Some teachers like to write it as 4.18. Some keep it as 4.184. And so this final answer will change depending on if you keep it at keep that 4 or you just drop the 4. But this is an approximate value. And that's how we solve this question. So much quicker and simpler when we just use this little trick here. Well, let's talk about bomb calorimetry and approach this question on it. So one thing about bomb calorimetry is that it is during a situation of constant volume. And it also measures the heat that is produced during a highly exothermic reaction. So a really great example is a combustion reaction. So anytime that you have mention of combustion reactions, you know that it is a bomb calorimeter that is being used. So let's deal with this question here. A 4.01 gram of glucose sample is burned in a bomb calorimeter, causing the temperature of the calorimeter to increase from 24.2 Celsius to 36.3 Celsius. The calorimeter contains 780 grams of water, and the bomb has a heat capacity of 895 joules per degree Celsius. How much heat was produced by this combustion reaction? So once again, I always default back to Q system equals negative Q surroundings, okay? So our system here is the glucose, and the surrounding is the bomb calorimeter. So typically, you would be inclined to say, okay, this is a Q equals MC delta T situation. Just plug and chug, MC delta T, find the missing, variable. In this case, it's asking for one of the Qs. So how much heat was produced by this combustion reaction, okay? So you can also write it again. Q reaction is equal to negative Q solution. If the word reaction is sort of throwing you off, you can also write it in this way, just like we did for the other questions, to make it a little bit easier to understand. But we can even write out what we have. So we have 4.01 grams of glucose. We also have 780 grams of water. The bomb has a heat capacity of 895 joules per degree Celsius. T1 and T2, we can write those out. So we have 24.2, 36.3. And it's asking for Q. So Q of the reaction. So this Q is essentially what we're looking for. So we need to solve what this Q solution is, essentially, is what we're going to do here. Okay. So if we look at Q solution, again, you might be inclined to say MC delta T because we have a mass here. And that is partially true. what I want you to pay attention to is the fact that you were given a heat capacity, capital C, not a specific heat capacity. So you can't necessarily just do MC delta T. You need to also do C delta T. That was the other formula that we saw at the beginning of this video. And so Q solution in this case, it is the bomb and the water. So it's going to be Q H2O plus Q of the bomb calorimeter. So that would mean that it is going to be MC delta T of the water and C delta T of the calorimeter. So that is Q solution here. So if we were to plug all of that in, we're going to get 780 grams C of water, 4.184, delta T, 24.2, plus C of the bomb calorimeter, so capital C, so joules per degree Celsius, times the difference in temperature. And so that 36.3 minus 24.2, that is 12.1 degrees Celsius. So that is what that is, 12.1 degrees Celsius. And so this is the Q solution, if you will, or Q surroundings. So if we plug that into our calculator, you're going to end up with 50,248.7 joules, or 50.2 kilojoules. Now, because Q reaction, or Q system, equals negative Q solution, or Q surroundings, we have to turn it into a negative value. So the answer is going to be negative 50,248.7 joules, or negative 50. That was horribly written. Negative 50.2 kilojoules. So depending on if it's asking for kilojoules or just joules, this is approximately the final answer. Again, if you keep that 4.184, or if you just make it 4.18, that will change this value by a little bit, but it should be around this number. And that's how we solve this bomb calorimeter question.